Hi, I'm Abhinav, and this is my implementation of the consensus Raft algorithm built entirely on Golang. In distributed systems, the hardest challenge isn't about storing the data. It is about maintaining consistency between each of the state machines when things go crash. So before we talk any further about the algorithm or the Raft, let us look at the problem statement. Let's suppose we have our bank server located in Mumbai, and for some reason, let's say due to a flood, the server is gone and the users for our bank cannot access the banking facilities. So what do? We increase the availability of the servers and then we place more servers geographically around the globe. Let's say one server is located in Mumbai and let's say another is located somewhere like Seattle. Okay. So let's suppose we have a user which has an initial balance of 500 rupees and that user at time t1 does a transaction of 400 rupees from his account, so its remaining balance would be 100 rupees. But uh, availability doesn't mean consistency, so the data in the Seattle server would still be showing balance as 500 rupees. And now at time t2, let's say the Mumbai server is down and it is not in service. But the other servers and the server in Seattle as well will still show the balance as 500 rupees, which is incorrect. So we do need a way somehow for all the servers to come to an agreement that at every given point, the state of all the servers would be same, which is called consensus or an agreement. This is where Raft protocol comes in. Raft is a consensus protocol designed to be easy to understand. Its sole goal is to make a cluster of servers look like a single, highly reliable machine to the outside world. It ensures that every node in the cluster processes the same command in the exact same order, creating a replicated state machine. In Raft, the logs are the single source of truth. The logs are stored in every state machine, or say every node. If someone takes the log and rerun all the logs in the order one by one, it would come to the final state of that current machine. So let's say we have our 5 nodes. How would we know which one to talk to? That is why in Raft, each node is in either of the three states: the leader, the follower, or the candidate. The leader is the node which you talk to, performs operation, and replicates the log along every node. And the follower is the one who passively replicates the leader. The candidate nodes emerges when the leader fails, and then the candidate nodes request for votes from other nodes. And if they win, they become the next leader, and if they lose, they again revert back to the follower. So let's say we are currently at term two. The leader is, let's say, the node S1. By the way, the term is defined as the period of time where a node was a leader. Let's suppose term 2 defines the period of time where the node S1 was the leader. If the leader changes in future, the term would also change accordingly. Okay, so the leader sends out heartbeat at every fixed interval. Let's say in 20 milliseconds, the leader sends out heartbeat RPC to every other node. That is how every other node keeps a track of, okay, the leader is still alive. So what happens if the leader goes down? So let's say our node S1 is down. So all the other nodes have a fixed, not fixed, all the other nodes have their own randomized timeouts. Let's say the servers waits for about 200 milliseconds before it starts complaining that, hey, where's the leader, it's dead. And the node S4 has that timeout of about 150 ms. So after that duration, let's say after 200 millisecond, the node S3 doesn't receive any heartbeat. So it knows, okay, the current leader is dead, we must start a new election, we must start a new term. So S3 is the first one to complain, so it becomes the candidate and votes for itself and asks votes from other nodes. It sends out request vote RPCs to all the other nodes asking for votes. And if this candidates obtain a majority of the votes, this will become the new leader for the next term. Okay, so what if what if uh, two of the nodes time out at almost at the same time? Let's say this one timed out at 205 millisecond and both of them became candidate at once. So what they'll do is they'll vote for themselves and ask for request vote RPCs, both of them, and whoever obtains the maximum number of votes becomes the next leader. So in situations like this, there is a possibility that both of the candidates receive equal votes. Let's say both of the candidates receives two votes, one from itself and one from the other node. And this also for this node also one from itself and one from node S2, and both of them receives equal number of votes. In situations like this, the the situation is a stalemate, and the election process moves on again. Like there happens a re-election, and the leader is chosen again. So let's see what we just discovered. Leader election. We elect one distinguished leader. All rights go to him. He's the boss. If he dies, we vote for the new one. Log replication. The leader accepts commands, write them to his log, and forces followers to copy his log. This ensures everyone stays in sync. Safety Raft guarantees that once a log is committed, it will never be lost, even if the leader crashes immediately after. Okay, so let's see all of this in action. Let's say we have a client who wants to communicate with the Raft cluster. So let us go to the cursor and yeah, this is our client started waiting to talk with the Raft, and let us spin up our nodes as well. So we went with a 5 node configuration. Well, as a node starts, it starts out as a follower. And as there is no current leader, the election timer runs out and it starts new election and a new term. Okay, so all of our 5 nodes are up. As you can see, the majority of vote went to the node 5 and node 5 became the leader for term 10. Now, what happens when any client communicates with the Raft as a whole? As you can see, the client's nearest node is S4, but the leader is S5. So what happens is, as the client communicates with S4, the Raft performs an internal redirect to the current leader, no matter from where the request comes in, from where all nodes the request comes in, it always performs a redirect to the current leader. So let's communicate with it. Let's type in hello. As you can see, it performed a redirect to the leader 5. So what happens is, let's say I typed in hello or for hello. So what happens is the request appends to the log of the leader. Mind my language here. The request is appending to the leader's log, not committing. Then the leader sends out append RPC uh, request to all of the other nodes. It sends append RPC to all of the other nodes. Basically, it is saying, hey, I've got a request. Please append this data in your own logs. So every node tries to append the data in its own log and responds with yes, that I have appended in my own log. When the leader gets the majority of the nodes to append them into its own logs, the entry here is committed. It is now then committed, and we've successfully reached consensus between all the nodes. Now, what happens if the leader goes down? Let's say we kill our leader. As we kill our leader, yeah, a new election starts out, and this time node 1 became the leader. So we now communicate with our new leader. Hello, new leader. How are you? Okay, so let's say after some downtime, our previous leader, the node 5, comes back online. So what it does is, in the next heartbeat, it fills its own log with the missing logs. Let's say node 5 is down and the new leader is S1, and we sent out hi, and hey, this is reflected in all the other nodes. Now, when the S5 node comes back alive, it takes this much data and appends in its own logs. So that is how the consensus is reached. Okay, so we have seen how this algorithm works and how they achieve consensus. But to this, there are many edge cases, like what if there is a network partitioning between the nodes and the leader gets drifted apart to the other side of the partition? And what if during an election, the follower has a higher term index than the candidate? In that case, the candidate steps down as a follower, and many other edge cases, which is implemented at the code level and beautifully described in the research paper In Search of Understandable Consensus Algorithm. Do check it out. So let's move ahead. Okay, so now let's talk about the conclusion for this algorithm. Raft lets us create a system which is highly consistent, fault tolerant, and it allows us to have a linearizable storage. It is definitely slow. The leader is the bottleneck because all writes have to be passed through the leader itself. So it is less performant. It is fault tolerant, but it doesn't replace two-phase commit, because Raft is made to create a distributed log where the distributed log is equal on every system. On the other hand, two-phase commit can actually deal with heterogeneous writes, meaning as opposed to just making a log, you can actually send different writes to different nodes. And what that allows you to create is something called a cross-partitioning distributed transaction. It is not performant, and it may be used for a very specific use case where you need the system to be consistent. It is better off as a nuanced piece of your code that specifically needs uh, to be consistent, and not a general database or system implementation. It is used internally or maybe some variation of it by Kubernetes, Cockroach DB, MongoDB. This was my implementation of the highly consistent Raft algorithm. I had built this project by referring to the research paper In Search of Understandable Consensus Algorithm. In future, I can use this Raft engine to build a proper system using maybe like command context, factory pattern, or any other design pattern. I have also added the GitHub repo link for this project in the description. Thank you guys.